Welcome back to the second day of our 12-day series. Today we deal with the number 11, and there are 11 coordinate systems where the Helmholtz equation is solvable in. If you have a point in space, how can you say where that point is in space? Well, you need a coordinate system, which will help you describe where a certain point is in space with respect to some reference point. One of the examples is the Cartesian coordinate, which you should already be quite familiar with if you've done maths before. Now, the second bit is the Helmholtz equation. The Helmholtz equation looks a bit like this. In the Helmholtz equation, there's this bit here, which could just be pretty much any function you want. Then you have some constant here represented by the letter k, and then you have this weird upside down looking triangle square. This bit here is what we call the Laplacian operator, and it's one of the operators that you'll find in vector calculus. But what you should know about this Laplacian operator is that one, it will differ between different types of coordinate systems, and it will involve some sort of partial derivative. And so since the Laplacian involves a partial derivative and the Laplacian operator is also part of a Helmholtz equation, this makes Helmholtz equations some sort of partial differential equation, which does in fact sound really cool. Now, as we said earlier, the Laplacian operator will look different between different types of coordinate systems. And this Helmholtz equation is only solvable in 11 of the coordinate systems, which I will list right here. Now, of course, there's loads more coordinate systems than these 11, but these 11 just happen to fit the criteria that we're looking for. Now, I could actually just go on and explain all the 11 coordinate systems, but the video will probably take way too long. So rather than explaining all of these 11 coordinate systems and bore you guys out at home, I'm only going to explain the 3 most commonly used coordinate systems out of these 11. So for anyone who wants an explanation on the other 8 coordinate systems, well, I'm really sorry. The 3 most commonly used coordinate systems that I'll talk about in this video is the Cartesian, the cylindrical, and the spherical coordinate systems. The first coordinate system, the Cartesian coordinate system, everybody's familiar with it. It's really simple. You've got 3 axes, you've got the x-axis, the y-axis, and the z-axis, and all you need to say is how far along the x-axis the point is, and then how far along the y-axis the point is, and then how far up the z-axis the point is. So for Cartesian coordinates, you just need 3 numbers, which says the distance of where the point is with respect to the origin in each of the 3 axes. Now, in cylindrical coordinates, it's slightly different. Cylindrical coordinates are really similar to polar coordinates. Polar coordinates is a way of describing where a certain point is on a 2-dimensional surface. To describe a point using polar coordinates, you will need the distance that the point is from the origin, and then you also need this angle, which is the angle that the line from the origin to that point makes with the positive x-axis. And so you need these 2 values to describe a point in polar coordinates. Cylindrical coordinates is really similar to polar coordinates. You just need to say how far the point is from the z-axis and what angle it makes with the positive x-axis, and then you just add an extra number, which is how far up or down it goes along the z-axis. So basically, it's like polar coordinates on the xy plane, and then you just say how far it shifts up or down along the z-axis. So you need 3 numbers instead of just the 2 like polar coordinates. Now, the reason it's called cylindrical coordinate is because if you have an equation like r equals to some constant and you plot that out on the graph, you'll get a cylindrical shape looking a bit like this. Now, to describe a point using spherical coordinates, you can do something very similar to a polar coordinate. So what we have for polar coordinates before, we have a line going from the origin to a certain point, and then we have to find the angle that line makes with the positive x-axis. And with that point being on the xy plane, now you can raise the point up to some certain height along the z-axis. The same thing as cylindrical coordinates, but to describe the point in spherical coordinates, you do different measurements. So to describe a point in spherical coordinates, you instead will need 2 angles and a distance. You'll need the distance of the line connecting the origin to that certain point, you'll need the angle that that line makes with the positive z-axis, and then you'll need the angle that the projection of that line on the xy plane makes with the positive x-axis. Now the notation and how you represent these three measurements might be different whether you're a mathematician or a physicist or which book you're reading off, but it's all pretty much the same idea. Now why is spherical coordinate called the spherical coordinate? Well, it's quite similar to why cylindrical coordinates are called cylindrical coordinates. If you let rho equal to a constant and you plot the graph of that, you'd get a sphere, which is actually quite neat. And spherical coordinates are in fact quite useful. Our longitude and latitude system is pretty much just spherical coordinates, and spherical coordinates is also used in physics quite a lot. And as I've mentioned earlier, the Helmholtz equation is solvable in the spherical, the cylindrical, and the Cartesian coordinate systems, along with 8 other coordinate systems, which I won't actually talk about in this video because it's in fact long enough already. Yeah, thank you very much for watching this video. Just don't forget, there are 11 coordinate systems where the Helmholtz equation is solvable in.